Hi everyone, we're very happy this week to have Hayden Lee from right across the courtyard. Hayden lives somewhere between cosmology and formal theory ideas. So I'm very happy to hear what he has to tell us whenever you're ready.
Yeah, thanks a lot. Thanks for coming. So today I'd like to talk about a paper we just put out last year with Xinkan Wang, and also ongoing work with Daniel Baum and Austin Joyce about the topic on the double copy in ADS and DS. Okay, so if you've been going to any amplitudes talks, then you probably are already familiar with or at least heard about the term double copy. So double copy, as I'll describe in more detail later, is a particular relationship between gauge theory and gravity. So basically it says that you can get gravity amplitudes by taking two copies of gauge theory amplitudes, and hence the name double copy. So this is pretty exciting because it means that so in general, computing gravity amplitudes are highly complicated. But what this relation says is that you can basically get gravity for free by starting from some much simpler gauge theory amplitude. So this double copy relation has provided a radically different way of thinking about gravity in some sense, and also gives a very practically useful tool for computing amplitudes. So which are constantly being used to compute gravity amplitude in the state-of-the-art computations. At the same time, it is pretty confusing why the double copy works at all, and nobody has like a deep explanation for where it's really coming from at a deep level. So there's sort of many directions that people are looking at to try to understand this double copy relation better. And especially over the last few years, one of the questions that people have been asking is whether this double copy relation is just some curious fact about amplitudes in flat spacetime, or whether it's something that is much deeper and something that generalizes to curved spacetimes like ADS and DS. Okay. So I've been also thinking about this question for some time, and very recently we've been able to make some progress on this. So I'd like to share some new results with you. Okay, so just so that everyone's on the same page, let me start with a very broad picture. So the objects that we're going to be interested in are going to be correlation functions in DS and ADS. And these are very interesting objects to study because they have many applications in high energy physics. So, okay, so on the one hand, correlation functions in the de Sitter space are very useful for cosmological studies. And that's of course because the current observations of the universe tells us that the early universe went through something like a period of inflation, which is governed, during which the space-time geometry is governed by a quasi-de Sitter background. And these correlation functions of quantum fluctuation that were formed during this quasi-de Sitter phase eventually give rise to actual correlation functions in the late-time universe that can actually go out and measure. So there's a lot of interest in trying to understand the shape and properties of these correlation functions living in de Sitter space and inflation. On the other hand, ADS, anti-de Sitter space, is a very interesting theoretical playground in high energy physics, which allows us to try to understand gravity in a rigorous way through this ADS-CFT holography. So in this picture, you can think of gravity theory in the bulk ADS spacetime as being dual to some conformal field theory living on the boundary in one less dimension, which allows us to understand the dynamics of an ADS field theory in terms of correlation functions that live on the boundary of this spacetime. In particular, recent development of the conformal bootstrap program has been very useful for both computing and understanding the fate of these conformal correlation functions. In fact, these correlation functions in DS and ADS are very closely related objects. Essentially, they're related by certain Wick rotations. Having said that, until recently, the two research programs in DS and ADS appear to be somewhat distinct, mainly because people used different languages to talk about these objects. So why is that? Well, first of all, the kind of questions that people ask in ADS and DS backgrounds are slightly different and have different motivations. But there's a more practical reason for using different languages. So in ADS, correlation functions are usually studied in position space. because that makes a total sense because conformal symmetry of these boundary correlators become manifest when written in terms of the position space variables. In contrast, correlation functions in de Sitter inflation are usually studied in the momentum space. And that's because these momentum space correlators that get feed into the cosmological evolution equations that are ultimately used to compute density perturbations in the late universe. Okay? But the downside of using momentum representation is that conformal symmetry of these boundary correlation functions. So imposing conformal symmetry amounts to solving a non-trivial differential equations in momentum space. And until very recently, we didn't know how to go about solving this differential constraints in momentum space systematically. But fortunately, there has been a lot of activities in both trying to understand the structure of these correlation functions in both ADS and DS from various perspectives. And now we seem to have a much better connection between these correlation functions living in different spaces. So just to give you some taste of some of the recent development, here is a non-exhaustive list of some of the things we've come to understand better about these correlation functions. So let me just highlight a few of them. So first, as I just mentioned, we now understand how to deal with the conformal symmetry constraint in momentum space directly, which has been very useful for understanding the shapes of cosmological correlation functions. Okay? So I'm going to mention some of these techniques later in the talk. We also now understand better what is the analytic structure of these correlation functions. So for instance, we now know exactly what kind of singularities and branch cut structures appear for these correlators at tree level. Moreover, we think we now understand the constraint due to unitarity and how it leads to a certain factorization behavior of this correlation function for certain kinematic limits. And last but not least, just like ordinary colliders, you can also think of inflation as a very energetic particle accelerator that produces very heavy particles in the early universe. And people, some including in this room, are developing a precise collider phenomenology for inflation with the goal of doing a precision test of various models of inflation and detecting new particles that might exist during the early universe. And the list goes on. Okay. So I just listed some of these properties of correlators that we've come to understand better. But notice that all of these concepts also appear in the study of scattering amplitudes, right? So that means that we can actually leverage the insights and the lessons that we have gained in the amplitude studies to understand these correlation functions. So somewhat curiously, we see that some of the properties of amplitude seem to generalize to a de Sitter and anti-de Sitter. And in fact, this is not a coincidence because these ADS and DS correlation functions, in a very precise sense, are a generalization of these flat space scattering amplitudes. Okay, so essentially, there exists a special kinematic limit that you can take called a flat space limit, in which these ADS and DS correlators precisely reproduce the scattering amplitude in the flat space limit. Okay. So I'm going to define what this exactly is in a few slides. But roughly speaking, this is like going to very short distances. Okay. In which case, these particles that are interacting are deep inside the bulk spacetime, which is far away from the curvature near the boundary. Okay. So in which case, all the dynamics of these particles are governed by flat space dynamics that is captured by the scattering amplitude. Okay. So that's roughly the picture. But now the point is that we now understand this limit very well. So in fact, demanding a consistent behavior of these correlators in the flat space limit is formulated as one of the strong consistency requirements that these correlators need to satisfy. Okay. So I told you all this nice recent development of these correlation functions, but it is still true that our understanding of these correlators is still very primitive compared to all the knowledge that we have gained for amplitudes over many decades. Okay. So what we'd like to do is to basically have a systematic development in our understanding of these correlation functions that kind of parallels that our understanding of amplitudes. So in that front, I'd like to ask the following two questions. Okay. So the first question I want to ask is, can we directly construct ADS correlators, ADS and DS correlators from amplitude away from the flat space? Okay. So in other words, is there a way of taking this flat space amplitude and go in the opposite way in this picture? Okay. So right now, the way we usually compute these correlation functions in DS and ADS are still somewhat complicated. So it would be extremely nice if you can simply take an expression of a given amplitude and then somehow directly lifting this to ADS and this illustrates. So I'm going to be more concrete about this question later in the talk. A related question is what properties of amplitude actually survive when we go to curve spaces like ADS and DS. Okay. So I just gave you some properties of amplitudes that seem to generalize to ADS and DS. But it would be very nice to know to what extent this is true, for what properties and how do they generalize and so on. Okay. So in this talk, I'll try to attempt to answer both of these questions. But for the second question, I'm going to focus on the particular property of amplitude called the double copy. Okay. All right. So as I already said, a very surprising property of amplitude is the so-called double copy relation between gauge theory and gravity, which is nicely summarized in this cool slogan that says gravity equals gauge squared. So this is conceptually very interesting, but at the same time also practically very useful for computing gravity amplitudes using this technique. So this statement is actually a mathematically proven statement that goes up to a certain order in perturbation theory. So that means that if somebody just handed you an expression for gravity amplitude or gauge amplitude, then you can simply go and check whether this relation holds. So mathematically, you can check this statement, but somehow what is lacking is the physical intuition for where this is really coming from. Okay? So people really don't know where this kind of relation really comes from at a deep level, and also how general this relationship is. Okay? So for instance,
sorry, Hayden,
yeah.
Could I just ask a question? Excuse me. On the gravity side, is asymptotically flat space-time somehow built into the statement of gravity equals gauge squared?
Right. Right now, the statement of the double copy is for amplitudes which live in the asymptotically flat space-time.
Okay. Yeah, thank you.
Yeah, but the question is whether this relation actually generalizes more general curved spacetimes beyond just the asymptotically flat spacetimes. Okay. So the kind of questions that people ask is whether this relation, first of all, in asymptotically flat spacetime, whether this relation generalizes to all orders in perturbation theory. Okay. That's one question. And another question is whether, this relation really generalizes beyond flat spacetime. Okay. So these kind of questions are being explored by many people in the field in all kind of directions. So the particular question that I'm going to focus on in this talk is this one. Does a similar double copy relation exist for DS and ADS correlators? Okay? And hopefully by the end of the talk, you will be convinced that the answer is positive. Okay. So here's the outline. So in the first part of the talk, I'll try to review some of the basic properties of these correlation functions. In particular, I'm going to highlight the boundary way of thinking about these correlation functions, and then introduce the so-called differential representation of this correlation. Okay. And this differential representation is going to play a crucial role in the double copy. Okay. And the second part, I'll show you how this differential language can be used to construct double copy construction in ADS and DS, first at the 3-point level and then at the 4-point level. All right. Is there any question before I move on?
So actually, I just want to follow up on that a little bit. So the asymptotic symmetry group for gravity is BMS, and for gauge theory, it's some infinite dimensional group smaller than BMS. Is there any known relationship, like one BMS is the square, or in some sense, of the gauge theory asymptotic symmetry group?
Yeah, I think somewhat related to your question is whether similar double copy relation exists for this kind of celestial amplitudes that live on the null surface of the Gaussian space. Yeah, I think that kind of question is also being explored by the people working on the celestial amplitude. And I think they have some sort of a double copy relation there as well. Yeah. I'm not sure how exactly it's related to the BMS group you're talking about, but they do have some formulation of the double copy for the celestial amplitude.
Okay, thank you.
I think that's done up to 4 point.
Done up to 4 point. Yeah, so. Okay. Let me move on. Okay. So yeah, again, the object that we are going to be interested in are these boundary correlation functions in ADS and DS. So you can think of these correlation functions as arising from some weakly coupled interaction in the bulk spacetime. These particles evolving intervals to form this correlation function on the boundary. And this boundary, in this case, is going to be purely spatial hypersurface. So I'm going to consider either de Sitter or Euclidean version of ADS. Okay. So in this case, the only difference between these two spacetimes is going to be this choice of the bulk coordinate given by, in de Sitter, it's given by the conformal time eta, and in ADS, it's given by the radial coordinate c. Okay. So the standard way of computing, we go about computing these correlation functions is by starting with the Lagrangian for this theory, and then computing Feynman or Witten diagrams, right? And for anyone who's done any calculation of these boundary correlators, you will know that starting at 4 points, the computations start to become rather complicated, or even at the 3-point level if you're dealing with the spinning particles. However, once you have done the computation and stare at the final answer, oftentimes the answer looks remarkably simpler than what you have actually gone through in the calculation. And this is kind of the general theme for computing this kind of boundary observables. So a similar story also exists for amplitudes. So you know that if you try to compute amplitudes in the usual Feynman diagram way, then oftentimes you have to go through a massive amount of complexities, but then the final answer is much simpler objects. Okay. So nowadays we use different techniques to compute this kind of boundary observables. So rather than looking at the bulk picture, the new philosophy is to try to get rid of the whole entire bulk spacetime picture and then simply focus on the observables living on the boundary. Okay? So we want to directly determine or bootstrap this correlation function living on the boundary. Okay. So yeah, so as I said, this is basically the spirit of the modern amplitudes and conformal bootstrap programs. So here we'd like to basically adopt the same strategy to try to determine these boundary correlation functions using some consistency requirements rather than following some bulk evolution. Okay. So there's a program called the cosmological bootstrap that has been being developed over the last 5 years or so that precisely try to implement this philosophy to do this kind of calculations. So the advantage of this formalism is basically twofold. First, there's a conceptual advantage that we are focusing on the final answers. So any kind of hidden structures in the final answers is actually much easier to see, which might be completely obscure in the Lagrangian description. But importantly, there's also a practical advantage that this formalism simplifies a lot of the calculation. Okay. So yeah, that's probably enough of the motivation. So let's actually dive into some actual details of this formalism. Okay, so as a very simple illustration of the structure of these correlation functions, we're going to consider a very simple theory given by this Lagrangian, consisting of this phi to the fourth and d phi to the fourth interactions. Okay. So now what we want to do is to basically compute the observables in this theory, so amplitudes in flat space and boundary correlators in DS and ADS. For concreteness, I'm going to focus on the DS correlators, okay? And also ignore all the coupling constants and all the numerical vectors for simplicity, just to highlight the kinematical structure of these observables. All right, so the amplitude calculation for, say, phi to the fourth interaction is trivial, right? We just have to integrate over this plane wave propagators, and then that gives the delta function that imposes the energy and momentum conservation, right? So here I'm denoting by P the usual D+1 dimensional Minkowski space momentum vector. We can also try to do the same calculation in de Sitter. Okay. So here, just for the experts, the object I'm going to be considering is the wave function of the universe. So the wave coefficient of the wave function of the universe, which is actually the big rotated version of the ADS universe. But this object is also related to the usual in correlation function in a straightforward way. So I'm going to slightly use abusive terminologies to code everything correlation. Anyway, this correlation function can be computed in a similar way. Okay, so in momentum space, if you look at the spatial part of the integral, it's exactly the same as in flat space. And that's because the spatial boundary that this correlation function stiff is purely Euclidean hypersurface. So we can simply Fourier transform this spatial coordinates on the boundary. Okay? But the time integral part is different. So here we have to integrate over these both boundary propagators. Okay? And we have to integrate it over some past infinity all the way up to the conformal boundary at A equals 0 hypersurface. Now, if you do this integral, then you basically find that the answer looks in this very schematic form. Okay, so again, the spatial part of the integral produces this delta function. Now, just imposing the spatial momentum conservation. Okay? But the time integral gives not a delta function, but some rational function of the energy variables. So by energy, I'm just defining this case to be the magnitude of this vector case. Okay? So here, if you look at the structure of this function, then it looks like there's a numerator given by some polynomial in the energies. And there's in the denominator, there's a k total that goes to some power. So k total is the total energy, okay? Just the sum over all the energies. So of course, we don't get a delta function here because there's no time transverse symmetry in the cosmological background. But nevertheless, we see that there's some interesting analytic structure this answer has. Particularly, it blows up when it becomes singular when you take k total going to 0 limit. Okay, so let's try to interpret what this means. So if you take so what happens when you take k total going to 0 limit here means that if you look at the integral, that means the integral actually blows up when you take k total going to 0 limit. Okay? And that actually happens because of the infinite contributions that are coming from minus infinity in the early time limit. In which case, this both binary propagator simply reduces to the usual plane waves as we do have in flat space. Okay. So what is physically going on is that sending this k total to 0 is just like imposing energy conservation by hand. Okay. In which case, we are having both the energy and momentum conserved, so we expect to reproduce the flat space dynamics in this limit. So this you can explicitly see in the integrals because all the propagators are reduced to just simple plane waves as we do have in flat space. So the integral structure becomes the same as in amplitude. The only difference is that the integral limit of time is from minus infinity to 0, not over the whole axis. That's why we don't get a delta function, but instead this kind of singular behavior. We can get a better idea about the structure by looking at this another example, d5 interaction. So again, the amplitude calculation is kind of trivial. We can just Fourier transform all of these spatial derivatives that turns into this very bunch of momentum factors. If you try to do the same calculation for the correlator, now that's not as trivial because we can only Fourier transform the spatial derivatives, but not time derivatives. Okay, so for time derivatives, we have to do this time integral explicitly in conformity of both the boundary problem. However, once you have done the calculation, somewhat remarkably, it turns out that you can nicely write down the answer in terms of these conformal generators acting on the previous solution that we found for the 5 to the 4th interaction. Okay. So here, conformal generator are really differential, some sort of a differential operators acting on this previous solution that we found. So this is like a simplest version of the differential representation of correlation functions. And you see the nice feature of this representation that it makes manifest to the connection to the structure of the amplitude. right? We simply replace these momentum vectors P with the corresponding conformal generators. We get the right answer. And also we can also look at the consistency condition that it should reproduce the amplitude in the flat space limit, okay? By which I mean sending this K total to 0. And we also nicely see that there's a singular behavior that goes as K total to some power, but the coefficient multiplying it is precisely given by the amplitude. Okay. All right. Just as a comparison, we can also look at the explicit expression of this in terms of the momentum vectors. Okay. So if you stare at this, it's somewhat non-trivial expression. But not so great thing about this representation is that, first of all, the conformal invariance of the answer is completely obscure in this formula, right? Also, the nice connection that we had to the amplitude structure is completely lost as well. Okay. So from this simple example, we kind of deduced that it is the differential representation is seems to be a more natural way of expressing these correlation functions. Okay, so this is what I just said. So ADS and DS correlation functions seem to have an interesting differential representation. Okay. So now what we would like to do is to basically derive the differential representation for more general types of correlation functions, which might involve exchanging particles or involving spinning particles and so on, because we want to eventually find the differential representation of the gluon and graviton correlation. Okay. So that's the idea. So it turns out that we can systematically go about doing this using the so-called embedding space formalism of CFTs. So let me briefly review what this formalism is. Okay. So the basic idea of the embedding space formalism is the basic observation that the boundary of ADS and DS can be thought of as being some section of the light cone living in one higher dimension of Minkowski space. Okay. So here in this picture, there's this light cone shown in blue. Okay, so this is a light cone living in one higher dimension than the DS and ADS space. But then there's a particular section of this light cone that corresponds to the boundary of DS and ADS. Okay. So here, the capital X describes the embedding space coordinates, okay, in this higher dimensional Minkowski space. And now this is related to this boundary coordinates, small x, through this method. Okay, when you specialize onto this section. Okay. So one of the nice things about using this embedding space formalism is that by going to this flat space in higher dimensions, you can now translate conformal symmetry, which acts non-linearly on this boundary coordinates, to Lorentz symmetry that acts linearly on this embedding space. So the constraint of conformal symmetry becomes much simpler to impose in this embedding space. And the conformal generator we saw before basically turns into these Lorentz generators that satisfy the usual commutation relation. And you can, if you want, you can also include the spin in the problem by also adding this dependence on this z variable, which plays the role of the polarization vector, okay, in embedding space. So basically, the idea now is to write down some manifestly Lorentz invariant quantities in embedding space, which is easy to do, and then use those expressions and then project onto this boundary so that it turns into some manifestly conformally invariant structures on this boundary. There's even more. It turns out there's even more benefit of using the embedding space formalism that was realized recently in these 3 papers here, which is about this correspondence between momentum vector and the conformal generator that we saw in this simple example. So it turns out that this correspondence between momentum and conformal generator is not restricted to the 4-point function example, but actually is completely general and generalized to arbitrary endpoint functions. So with this correspondence, we can now start translating a bunch of identities about amplitudes to the embedding space context. So For instance, you can easily translate this momentum conservation condition for amplitudes into embedding space, which now becomes the conformal word identity for a correlation function. So basically, the sum over the conformal generators acting on some correlator has to vanish as a consequence of conformal symmetry. There's also the analog of the mesh shell condition for amplitude. So the analog that in this case is the Casimir eigenvalue condition. Okay? So if you take the square of this conformal generator, that basically becomes the quadratic Casimir of the conformal group. And when you act with this Casimir on some operator, then it basically becomes gives this eigenvalue, which depends on the dimension and the spin of the operator that you're acting on. Okay. So it turns out, in embedding set we have this nice analysis between amplitudes and the conformal structures, and you will see actually a lot more of these errors throughout the talk. Okay. So another benefit of using this language is that these conformal generators give something called the Casimir equation. Okay. So here by C12, this is basically the quadratic Casimir L squared that corresponds to the internal operator O12 here. Okay. And that has the eigenvalue lambda O12. So here, by acting with this particular combination, C12 minus lambda O12, what it does is that it basically acts on this exchange diagram and then collapses this propagator. Okay, so this plays the role of the inverse propagator. Okay, so that cancels the propagator here and then basically turns this exchange diagram into a contact diagram. Okay. So you can think of this as the exact analog of multiplying by the inverse propagator S minus M squared for the amplitude that cancels the pole and then turns on exchange amplitude into a contact amplitude.
So question, can this map be the other way around? Can we like invert that?
Right, yeah, so I'm going to actually show that inversion procedure in the next slide. Yeah. Yeah, you can formally invert this operator and then move this onto the right hand side. So you can by acting with this inverse operator, you can start with the contact diagram and then generate the exchange diagram. Right. Okay, so now from this equation we see the nice analysis between Casimir operators and the Mandelson variables for amplitude. So here we can also translate this identity involving the standard Mandelson variables SD and U into this equation. Okay, so eventually we want to consider gluon and graviton correlation functions. So we also need to know how to increase spin of a correlation function in a way that manifestly preserve conformal invariance. Okay? And it turns out that there's a very nice formalism for doing this called the rate-shifting formalism. So this was first developed in this paper by Karatev, Khrushchev, and Stoffin, and then later imported to the cosmological context in one of our papers. So it turns out that you can construct this operator, which I'm labeled as E, that basically increases the spin of an operator by 1 unit. And then you can also construct an operator that simply shifts the dimension by 1 unit. Okay? And basically, by taking various combination of these rate shifting operators, you can start from any scalar correlation function and then turn it into a spinning version of it. Okay. So basically, how it works is shown in this representation. So you can start from a context scalar correlation function. Okay. And then you act with it with this operator that are defined as D, which is some combination of these rate shifting operators. That depends on the choice of these external operators here. Then you want to act with this inverse Casimir, which plays the role of the propagator in this context, which basically generates the exchange part of the diagram. Yeah, so this is basically your question. Okay, so the nice thing about this representation is that it exactly resembles the structure that we have for the exchange diagram for amplitudes. Okay. So here again, we can write exchange amplitude as a propagator multiplying some function of the Mendelssohn variables, multiplying the scalar contact diagram. Okay. So we see this very nice correspondence between the two pictures.
Can I ask a question? So like when you go back, maybe even one more. So one thing that is confusing to me is like you have a contact diagram here. You're acting some operator here, and you have a spinning guy to the left. But as we discussed, like sorry, and it's not clear to me, like so like the object in the left hand side depends on the choice of the gauge, right? So it's not like a gauge invariant quantity, for instance.
Well, I think we want to, so individual like a Feynman diagram, like a channel. Channel by channel is not gauge invariant.
Yeah.
So eventually what we want to do is to basically combine various channels of this kind of spin exchange diagram to form a gauge invariant object. So indeed, by diagram it's not gauge invariant.
Yeah.
So you want to find like a right combination of these operators and then combine with various channels.
So you want to get a full object.
Right.
Okay. Yeah.
Yeah. Thanks for the question. So basically we now have this very nice dictionary between the amplitude structures and the manifestly conformally invariant structures in ADS and DS. Okay. So here on the right column we have these differential operators in the ADS and DS side. The nice thing about these differential operators is now that even though they're originally constructed in embedding space, it's pretty straightforward to project onto this specific section of the light cone on the boundary of DS and ADS. And then if you want, you can also Fourier transform these operators so that they can also be used in momentum space calculations. So this differential formalism provides a nice way of connecting these various correlation functions living in different spaces. So here on the left-hand side, so we have these basic building blocks for scattering amplitudes. Okay, so these are basically functions of these polarization vector epsilons and momentum vectors and Mendelssohn variables. And now what you want to do is basically swap these with these corresponding way-shifting operators here. Okay? So these epsilons becomes E's, this little piece become these P operators. The Mendelssohn variables, as we saw, become Casimir operators, and the masses become these Casimir eigenvalues. And lastly, this momentum conserving delta function becomes this scalar seed function, okay, that the operator is supposed to act on. Okay. So I think we now have all the ingredients to try to construct now the gluon and gravitational correlation functions in this differential language. Okay, so let's now try to see how this works. Okay, so before looking at the correlators, let me first review the standard story for amplitude. Okay? So the standard way of computing things is again by writing down the Lagrangian and then computing Feynman diagrams for these interactions. Okay? So when we expand out the Lagrangian to qubit order, then we see that the graviton vertex is somewhat complicated, takes this form. But remarkably, when you compute the on-shell amplitude, then a bunch of these terms actually drop out of the problem, and we have this nice compact-looking amplitudes in the end. So if you compare these two expressions for the Yang-Mills and the GR 3-point amplitude, then you see that it enjoys the nice double copy relation between the two expressions. So explicitly, how you go from the first line to second line is that you strip off the color factor here, and then square the kinematic structure to get the graviton amplitude. Okay? So this is a simple manifestation of the double copy. But of course, it wouldn't be as impressive if just stopped working at this order. But of course, the power of double copy is that it's supposed to generate all orders at tree level. Okay. Yeah.
So since you're stripping off the color factors, it didn't really matter that you had like SU3 and you could have generic gauge group with some rank and it would still work.
Yeah, so the only thing that we'll be using is the symmetry structure of these color factors. So it doesn't really matter what kind of gauge group you're explicitly talking about. So in the end, we'll be stripping off all the color factors. So yeah, it works for any like SU2, SU3, and so on. Yeah, so the exactly the same thing works for the 4-point function. So here we'll be looking at this. So I'm calling it Yang-Mills, but it works for any gauge group. So here you can express the gluon amplitude, 4-point amplitude in this way. Okay, so it's split into these 3 channels, ST and U. So here, C's are the color factors. Okay, so consists of the structure constants of the gauge group. And here we divided by this propagators ST and U, and everything else I'm calling it to be this functions M. Okay, so these are called kinematic numerators. Okay, they are functions of the basic building blocks for the amplitudes. You may also ask what happened to the contact diagram, because there is a quadratic vertex in Yang-Mills theory. But what you can do is to basically reabsorb the contact diagram into these separate channels. Then you can easily do by simply dividing and multiplying by S and so on. Okay? So there is some freedom to how you distribute the contact diagram into these different channels. But what's very surprising is that once you express the amplitude in this way, then it seems that the color factors and the kinematic factors obey exactly the same algebraic identities. Okay? So here, when you sum over the color factors, it becomes 0, which is just a consequence of the Jacobi identity. But here, these n's are some very complicated function of these kinematic variables. But for some reason that we don't fully understand yet, the sum of the n's also gives 0, just like the color factors. Okay? So this is something called the Color-Kinematics Duality that was first noticed in the seminal paper by Burns, Carrasco, and Johansson, or BCJ. Okay, so one nice thing about this duality is that it's also invariant under any kind of gauge choice or field basis that you use to express the amplitude. So I told you that there's a freedom to how you distribute the contact diagram into different channels. Basically, that's another way of saying it is that amplitude is invariant under certain gauge transformations that shift these n's around. Okay. So in principle, you can use some arbitrary kinematic function omega to shift things around. But the nice thing is that this duality is actually invariant under this any choice of this gauge. Okay. So there seems to be some secretive things going on that gives this duality between colors and kinematics. And what we want to do now is to take this duality seriously and then try to replace things one with another. Okay? So now this is precisely the statement of the BCJ double copy construction. So basically, we want to take this expression for the gluon 4-point amplitude and then simply strip off the color factors, okay, and then square the kinematic factors here. Okay, so once we have done that, then the resulting object actually turns out to be the right amplitude for the graviton 4-point amplitude. And this is completely non-trivial because individual terms here is not gauge invariant. Only the particular combination of all of the terms gives the gauge invariant object. So the way things work is kind of still mysterious, but it turns out that this double copy procedure also works at arbitrary points at tree level and also has been generalized to multiple loops as well. Okay. So now what we want to do is to basically look for the generalization of this double copy in ADS and DS. Okay. So let's take a look at how things work in momentum space representation first. Okay. So it turns out that you can also similarly write this gluon 4-point amplitude correlator in this particular way. Okay. So here things are also split into different channels. These are the same color factors as before, but these tilted variables here are slightly different from the ones from the amplitude, and they differ by something that survives in the K total. Okay. So if you take this expression and take K total going to 0 limit, you will exactly reproduce the Yang-Mills or the gluon amplitude. But it differs from the amplitude by something that survives when you take K total finite. Now you can also try to analyze the exactly same thing, like whether it satisfies any color-kinematic duality. You'll find that in a generic gauge, okay, so there's also a freedom to how you distribute the contact diagram into different channels. But in general, this Color-Kinematics duality would not be satisfied in this case. Of course, because of the freedom of choosing how you distribute the contact diagram, you can also make arbitrary gauge transformation, choosing this arbitrary choice of this omega. Okay? And then you can always choose omega in such a way that it cancels whatever you had before for this sum of the tilde ends. Okay? By choosing it to be precisely minus whatever you had divided by this new Mendelson variables. Okay, so that gives in the new gauge the color-kinetic duality is satisfied, but still when you try to double copy this object, that doesn't give the sensible gravitational correlator, because now by dividing by this Mendelson sums, you're creating some superior singularity. Okay, and when you square these numerators, then these superior singularities don't cancel when you square them. Okay, so it turns out that the naive double copy procedure in the momentum representation doesn't quite work in ADS and DS due to the subleading terms in the flat exchange. So now the question is whether this differential representation actually provides the right language for the double copy in ADS and DS. We think that might be the case because these rate shifting operators that we just saw are the objects that precisely reduce to the amplitude building blocks, but then they also preserve the conformal invariance away from the flat system. Okay, so now the first task we have to do is first construct this differential representation of a correlator. Okay? And now we can make use of the dictionary that we saw before. So what we want to do is to basically take the amplitude, an expression for the amplitude for a given process, and then simply go through this bunch of replacements of the variables. So using the dictionary, we want to replace all the polarization vectors with this spin ranging operator E, the momentum with the operator P, Mandelstam variables with the Casimir operators, and all the masses with the eigenvalues. Okay. And then you want to take this differential operator combination and act on the scalar seed function. Now, this procedure is obviously not unique due to the reason that what we are basically doing is to turn these algebraic vectors into differential operators, which obviously don't necessarily commute. So there is some ordering ambiguity problem that you have to fix in going through this procedure. So a priori, it's not clear what ordering you should be using to go through this process. But in this new paper with Xingang Wang, we figured out what is the correct ordering that gives the correct correlation functions that have the consistent flat space limit when you take k total to 0. Okay. So basically, the right ordering turns out to be the one that places these spin operators to the left of all the momentum operators. So so physically, what we're doing is to first activate all the scalar operators of the scalar seed and then raising the spin at the very last step. And so we define this procedure to be some normal ordering procedure denoted by these columns. Another thing we have to do in going through this process is to properly normalize these wedge shifting operators. So even after normal ordering, it turns out that if you take the k total going to 0 limit, this wedge shifting combination produces the kinematic structures for amplitude, but only up to some proportionality constant. But now what you'll be doing is to combine a bunch of these wedge shifting combinations. But if you want this wedge shifting combination to combine in exactly the same way as for amplitudes, then you have to make sure that this coefficient constant coefficient to be 1, so that they have the same normalization as the amplitude structures. Okay? So you have to go through some normalization procedure as well. Okay, but that's it. So we now have all the ingredients as well as the procedure in how to construct this differential representation. Okay, so here let's look at the triple function case. So these were the amplitude expressions, and then now what we want to do is to basically go through these replacements and then go through this ordering procedure. So here we just want to replace all the epsilons with e's and p's with this big piece, and then act on the scalar seed function. So it turned out that this does indeed give the correct stripping function for the gluons. And what is the statement of the double copy in this case? Well, we want to just strip off this color factor as same as before, and then just take this kinematic part of the representation and then square this. Okay. So we square this, and then after squaring, we also normal order the operators, and then act on another seed function. Okay. So what we have to do is to also shift the dimension of the seed function. The reason is that the gravitons and gluons actually have different dimensions, so you have to account for this overall dimension by changing the choice of the seed function. But once you have gone through this procedure, it turns out that this gives the correct graviton treatment function in DS and ADS. And I just want to highlight how nice looking formula I think this is by showing you also the same expression that we had in terms of the same set of rate shifting operators just a few years ago. Okay. So here the notation T just means the stress tensor, which is due to the gravitons. But we see that by using some random ordering of the operators and then random normalization, we also get this random looking coefficients given the final answer, which doesn't have any apparent structure in it.
What are the what are those A, B's, and C's?
Oh, so A, B's, C's are referred to as these structures, which consist of various combination of the rate shifting operators. Okay, so I'm just using different labels. S's are like an E1.E2 and then things like that.
So basically, if you write it in a momentum space language, that's the expression.
Yeah, so this is still in the differential language. So yeah, if you act on the momentum space seed function, then you generate the momentum space stress tensor triple function. If you use the position space seed function, then you generate position space. Okay. Yeah.
I have a quick question about the previous slide. So this idea of taking the flat space double copy and doing the operator mapping, that commutes with doing the operator mapping and then stripping off the color factors.
Yeah, because yes, color factors are simply just a constant. As it doesn't affect this swapping procedure. All right, so yeah, in the final 5 minutes, I guess, let me quickly show you how the double copy works for 4-point functions. So now we do the exactly same thing as before. Okay, so we want to take the amplitude expression and then go through this bunch of replacements and then do the proper ordering of the operators. So now we have the same color factors appearing with the propagators replaced by these Casimirs acting on some 4-point seed function. The nice thing about this representation is that now all the nice properties that we had for the amplitudes basically get inherited in this representation. So you will find that this expression actually does satisfy the differential version of the Color-Kinematics Duality in any gauge. Okay, so we seem to have the same duality between color and kinematic factors here. So we can go through the double copy procedure. Okay, so same as the 3-point function K, what we want to do is to strip off the color factors and then square these kinematic factors, which are operators. Okay, and then after squaring, we want to order them properly. And then we also want to shift the dimension of the seed function. But now we have to do something extra, which is to also shift the eigenvalues in the denominators. Okay. And the reason is that the eigenvalues for the spin 1 conserved current due to gluons is actually 0, but the stress tensor actually has a non-zero eigenvalue that is due to gravitons. It turns out that this does indeed produce the correct structure for the graviton 4-point function. But at this stage, this remains slightly conjectural. So we've done a bunch of consistency checks that, for example, this has the right facet limit and produces the part of the answer correctly, but then we haven't so far been able to fully verify this formula. Okay? The reason has to do with this taking the inverse of this operator, which is kind of tricky to deal with. So right now, so if you had the answer known on the left-hand side, it is straightforward to check the answer. But right now, we don't have the right object on the left-hand side in a way that we can check the answer. However, we did check a very similar example. Okay, so this is the double copy of the Compton correlator. Okay, so we can look at the correlator involving two gluons and two scalars, which have this similar expression in terms of some slightly different color factors and the kinematic factors. But then we can go through exactly the same procedure as we did for the pure graviton case. That gives this following expression. So this time we do know what the left-hand side object is. So we were able to fully verify that this differential representation is actually correct procedure. Correct expression that arises from this double copy procedure. Okay, so let me quickly conclude. So we saw that we have this nice differential representation of ADS and DS correlation functions, which can be directly constructed from the corresponding amplitude expressions. So basically, we can take the amplitude and go through these replacements, and then order the operators, and finally acting on the correct, the appropriate seed function. Okay. And we saw that this is nice because this manifestly conformally invariant has the correct flat space limit and inherits all the nice properties of the amplitude. And as a result, this differential representation satisfies the color-kinetic duality and the double copy relation at both 3 and 4 points. Now, so I think this is like a very concrete step towards understanding the hidden structure of these correlation functions in ADS and DS. But also, beyond just having these nice looking formulas, we also want this representation to actually have a practical use for calculating something, right? That was the power of double copy for amplitude studies. So in order to do that, we actually have to address the following two questions. So first, we have to understand how to evaluate this differential representation. That is how to go from the right-hand side of the expression to the left-hand side. Okay. But once we understand that, I think this can be generalized to higher point functions as well as the loop diagrams, and then hopefully it will be useful for computing more complicated correlation functions. Yeah, I think that's it. So thanks a lot.
Thanks, Hayden. Do we have any questions?
So in the flat space case, there are generalization that include loops for this color kinematics.
Right. Yeah, so basically, the double copy for loop case works at the level of the interband of the loop integrals. So basically, you can also, if you look at the loop interbands, you can organize the loop interband in terms of these different channels, and then each channel has this color and kinematic separation, and then you go through the exactly same procedure.
No question. So now that you've understood this correct ordering prescription that's needed in more general contexts, is there some deeper understanding of what's really going on to be gained from that need for ordering in this particular way?
Yeah, so the basic set of operators that we are using are this basically this 3 differential operators. So I think we know how to order these set of these 3 operators properly. But it could be that if you consider more general types of correlation function, for example, like a supersymmetric version of this, then you might have to deal with some another like a fermionic types of rate shifting operators. In that case, we also have to figure out what the ordering we have to use. But I think for the bosonic correlation function construction, I think these are the only operators.
Right. Sorry, I guess I meant more if this tells you something deeper about how double copying, why it exists at all, why it's working at all. Right. You could proceed quite naively in the flat space case, and you see that in the curved space case, you need more care. can you, is there any insight from that the additional thought that's needed to get it correct in the, yeah, aside from, I mean, of course, it's good that you found the right prescription. That's so great. That's an achievement.
Yeah, somehow, yeah, all of these subtleties about operator ordering and stuff like that seem to vanish when you take the flat space limit, right?
Yes.
Yeah, because I think, yeah, well, ultimately, I think the statement of the double copy should have a generalization in DS and ADS, and understanding how the double copy works precisely in ADS DS. I think through this flat space limit, I think eventually can be used to also understand.
Of course, yeah.
It's better, but yeah, right now I don't know like what implications this ordering procedure has. You know, that's within the side. So.
Thank you. I think Sav has a question online.
Yeah, sorry. There was the very old string theory picture of, excuse me, the graviton as two copies of a gauge field, like a left and right gauge field. How much of the color kinematics, do you know how much of the color kinematics duality actually still works in string theory, was known to work beyond that original
We're talking about the KLT double copy.
So so there was the KLT double copy, which was sort of an older story. But does this go beyond that? I mean, does this have any implications or is known to be true in string theory?
Yeah, I don't know how the BCJ double copy translates to the string theory picture. Yeah, the way the KLT double copy works is slightly different from this BCJ double copy, where here we are kind of stripping off the color factor and squaring the kinematic factors, whereas the KLT double copy is about like squaring the whole full on gauge invariant amplitude, right?
Okay. So you couldn't even apply this procedure, you say, to a string amplitude. You wouldn't be able to.
Yeah, so if you take the original KLT double copy for strings, that takes 2 copies of open string to a closed string. If you take the alpha prime going to 0 limit of the KLT double copy, you reproduce the tree level double copy for amplitudes. But the statement you get when you take the limit is not the BCJ double copy, but something that involves squaring the whole gauge amplitude to generate the gravity amplitude. So I think, yeah, the procedure is slightly different. Makes sense. I think the BCJ double copy works more generally in this field theory case, because it also supposed to work at the loop order as well. I don't think it's clear to how to think about the KLT double copy procedure for loop amplitude or something more general than tree level.
Okay, very good. Thank you.
Any last question? Yeah, this.
In the last expression you showed, is there some distinction between going to DS versus ADS, or is it?
Yeah, so
basically the same.
Yeah, so here, yeah, I think the differential operators themselves are the same. So it matters what you take as the seed function.
Okay.
So if you take the ADS seed function with the correct phase vectors and stuff like that, you will generate the ADS version of the correlator. Yeah, if you have a different seed function with a slightly different phase vectors, you will generate the distilled version.
Can we go back to the ordering again? Yeah, is there like any kind of intuition that you can give why this ordering worked as opposed to like a different ordering? Like what was was there some cancellation or?
Right. Yeah. So the ordering here is the one that places all the spin operators all the way to the left, so they act lastly after acting with all the scalar operators. Yeah. So if you consider like a different ordering, what happens is that somehow this P operator doesn't act so nicely when it acts with the E operator. Because this E operator contains a bunch of spin factors. When you act with the scalar operator, the spin factor is generates some spurious terms. It doesn't reduce to the nice amplitude in the flat space limit. So you generate some more stuff. So this mapping is not is no longer 1-to-1.
And also like the E dot P like is 0, like, so is that true in like the operator languages, I guess?
You mean this error?
Yeah, oh, yeah, sure.
Yeah, so this is this correspondent is supposed to, so this supposed to act on some correlator.
Yeah.
So when you act on the correlator and then take the successive limit, you will find that you will find that this correlation factor actually multiplies some K total singularity. So so this statement is about taking the full correlator after acting on the seed function and then taking the separating the singularity term with the correlation term.
And how about the normalization? Is that like a trivial thing, or is that like, is that
For some operators it's trivial, for some operators it's not. Actually, for the spin operator it's kind of trivial, for the momentum operator it's not so trivial.
Thank you.
Great, let's thank Hayden again.